we've been looking for dark matter for a long time. And one of the places where we can look for signatures of dark matter are the cosmic ray fluxes. And if we consider dark matter that annihilates into final states that include electrons and positrons, then we can look at the cosmic ray electron and positron spectra to search for dark matter signals. The potential problem there is that there's another type of source that would produce a similar signature, which is pulsars. And in this talk, I'm going to show you how we can distinguish the two and then be able to uniquely identify a dark matter signal if we find it. Okay. So just for context, this is, you can see here the cosmic ray electron and positron spectra as measured on Earth. And you see that the positron flux is about an order of magnitude below the electron flux, which is because it's much less abundantly produced in interactions. And this makes it especially interesting to look for signatures of new or rare processes such as dark matter. And you can also see that at higher energies, the positron flux rises compared to the electron flux. And there we think this is because of a new source of contributions from pulsars. So on the plot on the right, you can see how we currently model the positron flux. So at lower energies, we have positrons that are produced in secondary interactions from other cosmic rays. They are not important for this talk. And then at high energies, the best explanation currently is that there's a contribution from nearby pulsars that produce high energetic electrons and positrons. And then potentially there's a contribution from dark matter that annihilates into electrons and positrons. And this would produce this very sharp feature with a cutoff that corresponds to the dark matter mass. Now, these spectra that I showed you are the ones that we measure at Earth. But the spectra at which the sources inject the electrons and positrons look very different. And what happens in between is very important to model if we want to understand precisely how the source works and also what contribution we would expect from a source when we measure it at Earth. And electrons and positrons, they lose energy very quickly as they propagate through the galaxy. And the two important processes are synchrotron radiation, so that's just energy losses in magnetic fields, and inverse Compton scattering, which is an interaction of an electron with a photon. Yeah, so now I'm going to explain to you how we get how we model the spectrum of an individual pulsar. So a pulsar is a neutron star that rotates very rapidly and converts some of this rotational energy into electrons and positrons, which means that when it's still very young and rotates very fast, it injects a very large fraction of the electrons and positrons that it injects over its entire lifetime. So we get this kind of burst-like injection almost in time. So we get a lot of particles at once, and then these are injected at a range of different energies like GeV, TeV, up to PeV energies. But the way energy losses work, as you can see in this plot, is that high energy electrons, let's say a 1000 TeV electron, loses energy much faster than a lower energy, for example, 1 TeV electron, as you can see in this plot. And this combination of having a lot of particles at once and then these high energy electrons losing energy faster than the low energy electrons translates to what we see in the right plot, which is the spectrum of a pulsar at different pulsar ages, so different times that these electrons had time to cool. And when the pulsar is still very young, okay, now I see how this happens. Yeah. So this one in the top, you see that we see this feature from the pulsar, and then as the electrons have more time to cool, this feature moves to lower energies, and then these high energies electrons move up with the lower energy electrons in energy, so to speak. And this is how we build up this sharp feature, and yeah, this typical feature that we get from a pulsar. Anyway, so we get this sharp feature, which is a bit unfortunate because also from dark matter we would expect a sharp feature. And this feature from the pulsars we get from the energy losses. So we have this potential degeneracy from the pulsar feature and the dark matter feature. And to understand why we get this, and also to be able to distinguish the two, we have to look more closely at how we model energy losses. Okay, so this is the energy loss rate equation that's typically used to calculate energy losses. The details are not really important, but you can see there's a term for the synchrotron energy losses and a term for the inverse content scattering energy losses. And then what is important about this equation is that it treats energy losses as a continuous process. Now the question is, are these energy loss processes really well described by a continuous equation? So if you look first at synchrotron radiation, we can use this equation to estimate what the average energy loss in one interaction is. If we take some typical values and look at an electron of 100 TeV, then the energy loss in a single interaction is 1.8 kilo electron moles. So that's very little. And also synchrotron losses happen constantly because electrons and positrons follow the magnetic field lines. So this is a process that takes only small amounts of energy at once away, happens frequently. So it seems very reasonable to describe this as a continuous process. Then for inverse Compton scattering. So this is a process where a high energy electron or positron scatters with a photon from the interstellar radiation field. So that's, for example, a CMB photon or a starlight photon. And it transfers some of its energy to that photon. Now, as you can see in this equation, this interaction is further suppressed at high energies due to kinematic reasons when we have high electron and high photon energies. And this is called Klein-Scheiner suppression. I just mentioned it here for completeness. Now, if we also look at some typical numbers shown in this plot, or I also wrote them down, what is the average energy loss per inverse Compton scattering interaction? So for a 1 TeV electron, this is less than 1%. For a 10 TeV electron, this is around 4%. And then for a 100 TeV electron, this is 10 TeV, which is 10%, which is quite a significant fraction. If we remember, for the synchrotron radiation, we had keV energy losses. So you can see here that for inverse Compton scattering, energy losses are much more significant in a single interaction, and also they happen much more rarely. So we can see here that while this continuous energy loss rate works really well to describe synchrotron radiation, it doesn't work well for inverse Compton scattering, because inverse Compton scattering is a very stochastic process where energy losses are rare and can be very catastrophic. They can take away a very large fraction of the electron energy at once. So then to investigate the impact of this stochastic inverse Compton scattering, we set up a Monte Carlo simulation, and it just works like this. So we create a positron at some initial energy, or electron, it doesn't matter. And then for each time step, we use the continuous equation to calculate the synchrotron energy losses. And we have a Monte Carlo to determine if an inverse Compton scattering interaction happens and at what photon energy. And then if one happens, then we calculate the energy loss using another Monte Carlo, and we get a new positron energy, and we repeat this until we have reached the time that we are interested in, for example, the pulsar age. Now, here are some results. So in this plot, I'm showing electrons that were all injected at the same energy, 10 TeV, and cooled for the same amount of time, 342,000 years, which is a typical pulsar age. And you can see on the x-axis, we have the average energy that's lost per inverse Compton scattering interaction for each electron. And you can see there's a large spread of average losses. And then on the y-axis, we have the final electron energy after this amount of time. And you can also see that there's about a 30% spread. So we get this distribution of final energies. Also, some other numbers. Around this time, these electrons only, on average, have 110 interactions. So that's not very much. And then energy losses, they can take small amounts of energy away, but also very large amounts. So inverse Compton scattering is really a very individual process, so to speak, for each electron. And yeah, so we get this distribution of final energies. And if we think about the continuous approximation, then all positrons are treated in exactly the same way. They will cool down to exactly the same final energy So we get this one energy compared to this distribution of energies. And now if we go back to our pulsar model, we get this result. So the blue line is what we expect from the continuous equation where we get this sharp feature. And then the orange one is our Monte Carlo model where we take the stochasticity of inverse Compton scattering into account. And you see that this sharp peak disappears, and then also the cutoff is much smoother. So that we can conclude that pulsars cannot produce sharp features. Here's just a preview of some things I'm working on, because for this previous paper, we were only able to do this for one pulsar as an example, but now we're running some more simulations to get this for any type of pulsar spectrum and model. Yeah, but you can see I am still running for more statistics. So I guess like 1 million CPU hours from now, we will have a paper. Anyway, I think you can see that pulsars won't produce a sharp feature because of this stochastic inverse Compton scattering, which is really convenient because now dark matter is the only signal that we know that would produce a sharp feature, so we can distinguish the two. But now you might be wondering, if we treat inverse Compton scattering stochastically and it makes the sharp pulsar spectrum smoother, doesn't the same apply to the dark matter signal? And the answer is no. In fact, the opposite happens. The dark matter signal becomes sharper. And to understand this, we have to look at how electrons and positrons how pulsars and dark matter inject electrons and positrons differently. So for pulsars, it's almost a burst-like injection in time. A lot of electrons are produced at once. And then they are produced at a distribution of energies following a power law. For dark matter, this is all the other way around. So in time, they constantly produce electrons and positrons because they annihilate always around us. And the energy spectrum is peaked instead. So based on what is peaked, the injection time or the injection in energy, the effect of stochastic inverse Compton scattering changes. Yeah, so in this plot, I want to point out again that energy losses are very large in the first interaction. So for, let's say, 100 TeV electron, we get around 10% energy loss. So we can see that inverse Compton scattering energy losses happen rarely, and once they happen, they take a very large fraction of energy away, which becomes more important now when you look at the dark matter signal. And then also I have this plot that shows the energy, or that shows how the lost time, the time that it takes to lose a certain amount of energy. In the solid line, we have the continuous approximation, and in the dashed line, we have the stochastic model. And you can see that energy losses take longer in the stochastic model. And this is because in the continuous model, energy losses happen immediately. The electrons are produced and they lose energy even to some average inverse Compton. But in reality, it is not the case because it might take for 100 TeV electron on average 5,000 years until they have their first inverse Compton interaction. And then they lose a large fraction of energy. So really what happens in the continuous model is that all electrons lose a bit of energy all the time. But in reality, in the stochastic model, some electrons or like a few electrons lose a large fraction of energy sometimes. Okay, so going to the dark matter signal. So the blue one, again, is what we expect from the continuous approximation. And then the red one is from the stochastic model, where we see this increase of the signal near the dark matter mass, near the energy that the particles were injected at. And this is exactly because once the electrons are produced, they sit for a while on the energy until they have their interaction. And in this case, it's about a factor of 2.6. But this also depends on the energy resolution. So if we have a better energy resolution, this increases. So in the plot that I just showed, which is, okay, Control N, I will never forget after this conference. Okay, so this top plot is the plot I just showed, and there we used a 5% energy resolution. If we use a 1% energy resolution, which is quite reasonable. It's expected for experiments like HERT in a few years from now. We can see that this enhancement, we can resolve it even further. So then instead of a factor of 2, it's a factor of 5. And then this also translates to lower energies where the average energy loss in the first inverse content scattering interactions is smaller. But if we have a good energy resolution, then we can still resolve this and have this increased detectability potential. And then on the plots on the right side, I'm just showing different magnetic field models that determine how much synchrotron losses there are. And then the different dark matter energies that we looked at. So you can see it's usually a factor of a few that is enhanced. Now, we also looked at what this looks like for dark matter annihilation into a pair of muons. So then we produce muons and they will immediately decay into electrons and positrons, which means that now that the electron injection spectrum, it is not as sharp anymore, it's a bit more smooth. So the effect should be less strong. And as you can see here, at the highest energies, we still get a factor of about 2, but then also it doesn't happen at the peak, so it will be harder to observe. But what instead is interesting to observe about this is that if we were to fit this to a signal that we observe, we would underestimate the dark matter mass in the continuous model, because you can see this shift between the two models. And then if we go to like annihilation to tau, this would be even less, because the injection is more broad. Yeah, this is my summary. So I showed you here that if we treat inverse content energy losses precisely as a stochastic model instead of using the continuous approximation, the pulsar feature that we thought would be sharp becomes much smoother, and the dark matter feature is enhanced. And this is quite nice because now we know that if we see such a sharp feature somewhere in the electron or positron flux, it must be dark matter, because we don't currently have any other explanation for this. So I guess now we just have to find a feature and then, yeah, that's it.